you can see in this diagram that our parabola is opening towards the focus and away from the directrix. And there are also some important properties involving the focus and the directrix. So let's look at this in a dynamic parabola, one that we can move around and investigate with. So here I have a parabola, and here's my focus, and here's my directrix. And I can move the focus around, and you see as long as I keep it about the same distance from the directrix, I'm not changing the parabola very much. But as soon as I start to move away from the directrix, the shape of my parabola begins to change. And it's getting wider and wider. And then as I come back closer to the directrix, my parabola becomes more narrow. Now, why is this? Why do we get this change in the shape of the parabola when I move the focus? Well, we have some distances that we can look at here. And the orange segments, let me move a little bit further out so you can see it a little better. These orange segments are marked as being equidistant, or the same length, because they are. So that means that my vertex is equidistant from the focus and the directrix. And that equal distance is what changes the shape, because as I get closer, I mean here in this, at this spot it may not look like it makes much of a difference, but I can take this point that right now is on the vertex and I can move it to any point on the parabola. And no matter where I move it, this distance will equal this distance. So let me move it way out. As the focus moves closer to the directrix, if I move this point really far from the focus, in order to be the same distance from the directrix, it has to be a bit more narrow. If I now were to make it a wide parabola, actually let me get my point in first before I do that. If I make it a wide parabola, and that equally distant property still remains regardless of where I move this point, now the parabola changes shape because it's maintaining these equal distances. This is another way to come up with the graph of the parabola. And this is called the geometric construction because we're using geometric properties. And it's based on where the focus is and where the directrix is. Now I can also move the directrix. Right? And we see the same thing happening as when I move the focus. I can move it on the other side. And now my parabola is opening down. But notice I still have these segments, and the distance remains the same regardless of which point on the parabola I choose. All right, so that's why we can use the focus and the directrix to write the equation, because in this construction of a parabola, the geometric construction, it's really dependent on where the focus is and where the directrix is. That's what gives me the shape of my parabola. So what we're going to be looking at are those equal distances. Remember we said it's an equal distance from the focus to the vertex, and then from the vertex to the directrix. And that value, that's called the focal length. And the variable that we use to represent focal length is P. And that's going to become important when we write our equations. All right, so let's try one. So I put a graph in here, or X and Y axes, just so that we can look at it. You don't have to graph it. You're not asked to graph it in this problem. But I think when you do the first few types of these problems that it helps to have a graph. So my focus is at 2, 5. So 2, 1, 2, 3, 4, 5. And my directrix is at y equals 1. So from this picture, I know that my parabola is going to open up because my parabola is going to open towards the focus. So if I want to find the vertex point, which is important in my equation, then I need to find the midpoint of this segment, right? Because I know my vertex is the same distance from the focus as it is from the directrix. So if you have a graph, it's much easier to do. Right? You can see what point would be right in the center. If you don't have a graph, then what you're looking for is the midpoint between y equals 1 and y equals 5. You can find that by taking an average. 5 plus 1 is 6, divided by 2 is 3. For the x-coordinate, you just use the same x-coordinate as the focus because it's on that same vertical line. So my vertex is going to have an x-coordinate of 2 because it's the same as the focus, and a y-coordinate of 3 because it's the average of 5 and 1. If you look at it graphically, again, you can see it right away. You don't have to do any calculations at all. You can just see where it is. All right, so we know that the vertex is 2, 3. The other thing we need to write our equation is P. Remember, P is the focal length. P in this problem is this distance right here, and it's the same, right, because we have those equal distances. This is 2, this is also 2, so P is 2. The way that that's going to help us is, remember, we have an A that's out front of our parentheses in vertex form, and that A is equal to 1 over 4P, which means here that A is going to be 1 over 4 times 2, or 1/8. So now we're ready to write the equation of the line. So let me go back and just write the form with all the variables in. This is vertex form. It was y equals a times x minus h squared plus k. And hk is the vertex. So that means that if I'm going to put the vertex in, this is going to be my h, and this will be my k, and this is a. So I'll have y equals 1/8 x minus 2 squared plus 3. And that's it. That's the equation given this focus and this directrix. All right, let's try one more. It's pretty straightforward. So this time our focus is at -1, -2. So -1, -2 would be here. And my directrix is at y equals 3. So that means my parabola is going to be opening down this time because it's going to be opening towards the focus. So let's find the vertex first. I'm going to draw a line segment connecting, I can make it dashed or solid, connecting my focus to the directrix. And I'm going to find the midpoint of that line. Well, this line segment is 1, 2, 3, 4, 5 units in length. So half of that would be 2.5. So right here would be the midpoint. Again, the other way you can do that So what I got here was 1/2. The other way you can do that is by averaging these two values. So -2 plus 3 divided by 2, that would be an average. That would give me 1/2. That's my y value. The x value of my vertex point is the same as the focus. So that means my vertex is at -1/2. And that's exactly where I found it here in my diagram, in my graph. So that means the parabola is going to look, something like that. But now let's get an equation. So now I need P, because P is what's going to give me the information to get A. So P is this distance right here from either the vertex to the directrix or the vertex to the focus. Doesn't matter because the distances are the same. So just choose one. And we know that that's 2.5. Now we're not going to write 2.5 because we really want to have it as a fraction. We really want to stay away from decimals from now on. So instead of writing 2.5, I'm going to write that P is 5/2 because that's the same thing as 2.5. It's just the improper fraction form. So for A, I have to do 1/4P, which is 1/4 times 5/2. Remember, multiplying fractions, don't let this mess you up. You can write it as 4/1 if that helps. And then you just go straight across. 4/5 is 20. 4 times 5 is 20. 1 times 2 is 2. And now that simplifies to 1/10. So that's my A. Once I have A and I have my vertex point, I can write the equation. So here's the equation with variables first. A, and then we have x minus h squared plus k. This is my h, this is my k, and this is part of my A. The other part I have to add in is I have to put a negative out in front because this parabola opens down. And again, the way that I know it opens down is it's always going to open toward the focus and away from the directrix. All right, so I get y equals -1/10 x minus -1 plus 1/2. So I'm going to simplify that a little bit more. -1/10 x plus 1 squared plus 1/2. And there's my parabola equation. And that's it. It's really that straightforward that I'm not going to say simple. It's not exactly simple, but it's very clear. You find your vertex, you find P to get A, and then you plug them both in.